Make no mistake, this guy doesn't understand math, and I'm not even going to talk about all the other stuff he's gone on about. This video isn't about why he's right, it's about how you might be wrong about why he's wrong. Also, if you know even a little bit of abstract algebra, nothing in this video will be new to you, but you should watch it anyways because I like money. So, for those of you who are not aware, about 1,000 years ago in internet time, there were a bunch of people talking about how this famous person I'd never heard of called Terrence came up with a revolutionary new form of math where 1 times 1 equals 2. He posted his original paper about this on Twitter. We'll talk about it later. For now, what I want to focus on is how people typically responded to this.
So when you're saying times, when you're using multiplication here, you're talking about the groups of something. So one group of 1 is 1.
Let's review what multiplication is. Multiplication is an elementary arithmetic operation which is essentially repeated addition. 1 times 1 means you write 1 one time. So it's 1. There's nothing to add. His revolutionary discovery is just him being dumber than a toddler.
The problem I have with these arguments is that they can be levied against other kinds of multiplication that are now widely accepted. -1 times -1 is 1? How can you even have negative numbers, let alone add them to themselves -1 times? I times I is -1. How can you have I of something, let alone add it to itself I times? I isn't even a real number. Matrix multiplication? There's a way to add matrices together, but how can you repeat this process a matrix number of times? Despite these objections, mathematicians know that these are perfectly valid ways of doing multiplication. We can also visualize them quite clearly. Multiplication by -1 can be visualized as reflecting a number to the other side of the number line. Multiplication by I can be visualized as rotating a number by 90 degrees. And matrix multiplication can be visualized as performing one linear transformation and then another. But if there's no repeated addition in these situations, then how do we know whether or not something is a multiplication or not? Well, I'm not too familiar with the history, but what I do know is that eventually mathematicians did come up with a list of properties that multiplications should have. First, multiplication should be associative, so x times y times z is the same thing as x times y times z. And second, it needs to have another operation it distributes over, which is typically called an addition. The addition itself needs to satisfy certain criteria, but since we're only going to work with the normal addition you're used to in this video, we don't need to worry about it. So if we want to show that it's impossible to have a multiplication of the usual numbers that we're used to, I'll stick to the rationals just for simplicity. Where addition still works like it usually does, yet 1 times 1 equals 2, we need to prove that an associative operation that distributes over addition, where 1 and 1 make 2, cannot exist over the rationals. One way to do this is by assuming that such an operation does exist and showing that it leads to a contradiction. Let's try it. Suppose that we have an associative and distributive operation. Let's call it star instead of times to avoid confusion with normal multiplication since we're going to be using it at the same time, where 1 star 1 equals 2. Let us now see what happens if we try to star together any two random rational numbers. Well, every rational number is just some integer divided by another, so let's write them as a over b and c over d, where a, b, c, and d are just integers. Let's say that a and c are positive and that only b and d may be negative. Keep in mind that this division cancels out only with normal multiplication, not star. Okay, so we can express this as a times, normal times, 1 over b, all of c times 1 over d. Now, because we're back to boring multiplication with integers as repeated addition, we can replace this with 1 over b plus plus 1 over b with 1 over b there a times. All of 1 over d plus plus 1 over d with 1 over d there c times. Now, we assumed that star is distributive, so let's distribute this term into this one. This gives us a terms worth of 1 over b star all of 1 over d plus plus 1 over d. Now let's distribute again, and we end up with 1 over b star 1 over d, c normal times, itself a normal times. So we end up with ac times all of 1 over b star 1 over d. Okay, that was a bit confusing, because we had a lot of distribution and two different multiplications going on, but we finally got something nice. So what is 1 over b star 1 over d? Well, now we go to our other assumption. We said 1 star 1 is 2. But 1 is just b times 1 over b, or d times 1 over d. So we do the same trick again. Here we have b terms worth of 1 over b. Here we have d terms worth of 1 over d, and we can distribute again. Here we have b terms of 1 over b star all of 1 over d plus dot 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 plus 1 over d. Distribute again, and we find that we have a grand total of bd terms worth of 1 over b star 1 over d. Now this is all equal to 2, so a little cancellation shows that 1 over b star 1 over d is just 2 over bd. Now let's go back to p star q. That was just ac times 1 over b star 1 over d, which is just ac times 2 over bd, which is just 2 times a over b times c over d, which is just 2pq. And look at that! Instead of finding a contradiction that shows star cannot exist, we found an exact formula for what this operation must look like in terms of typical multiplication. We even have a multiplicative identity. 1/2 takes the role that 1 used to have, as 1/2 star 1/2 is 1/2. So there you go. Multiplication where 1 and 1 make 2 is possible. So does this mean Terry's incredible claims about revolutionizing math are true? Well, no. This operation is actually extremely boring. You can see from the formula itself that it's literally just normal multiplication with a pointless factor of 2 added onto everything. You'll also note that the original paper that Terry published on the subject has a bunch of additional multiplication facts, which would not work if 1 times 1 were equal to 2. Since we already showed this is the only way to make 1 times 1 equal 2 in the rationals, and if we apply it consistently we get different results. Actually, this operation is so boring that there's a sense in which I can say it's exactly the same thing as normal multiplication. But before I can explain that, I need to talk about something else. A long time ago, before TikTok was invented and this number was funny, there used to be a social network called Vine, which had more or less the same basic idea. One of the videos that became popular on that platform was this one.
You stupid.
They're not.
What's 9 plus 10?
21.
You stupid.
Now, the humor, of course, is that the child is confidently wrong. In typical arithmetic, 9 plus 10 is 19, not 21. However, as popular channel Mind Your Decisions pointed out, it is actually possible to make this statement true if we change from using base 10 on both sides of the equation to using different bases on each side of the equation. We can then work out infinitely many pairs of bases where this works out. They correspond precisely with the integer points on this line, with x coordinates strictly greater than 9. Now, if you don't know what that means, don't worry. I only bring this approach up because I actually don't like it. I don't like it because it requires changing which numbers these symbols actually refer to. What I would like is a notion of addition in which I can say that this quantity, regardless of how you represent it, plus this quantity, regardless of how you represent it, genuinely gives you this quantity, regardless of how you represent it. Fortunately, there is a way. Consider the 12-hour analog clock. Notice that adding hours to the clock gives us a kind of addition that is different from what we're typically used to. For example, it looks like if the clock is at 12, and we add 12 hours, we get 12 again. In this system, 12 is basically 0, since 0 plus 0 is 0. Furthermore, if we add 2 to 11, we get 1. In this system, 13 is basically 1, which makes sense since it's 1 more than 12, which is 0, and 1 is 1 more than 0. This system of arithmetic is called the integers modulo 12. More generally, we can talk about the integers modulo n, where n is any integer greater than 1, as being basically the same thing, except it only goes from 0 to n minus 1. Let's take a look at the integers mod 2. Well, we only have 0 and 1, but we can still add bigger numbers together in this system by just breaking it down into adding a bunch of 1s. Let's see what 9 plus 10 would be then. Starting from 0, first we add 9 ones, and then we add 10 ones. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We end up at 1. Great. Now let's see what happens when we just add 1 to 0 21 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Would you look at that? We get the exact same result, 1. This fact is usually communicated by saying that 9 plus 10 is congruent to 21 mod 2. Now, this integers mod 2 system might seem really strange to you if you haven't seen it before, but it's actually not as unfamiliar as it seems. Let us consider a system where the only numbers are 1 and negative 1, and the only operation is typical multiplication. We can create a multiplication table that looks like this. Now, let's compare it to the addition table we get in the integers mod too. You might notice that both tables look pretty much identical. If we swap out the 0 with 1, the plus with multiplication, and the 1 with -1, everything looks the same. The underlying structure isn't any different. The only thing that's different is the labels. Whenever this happens, we say the two structures are isomorphic. In this function, that tells us how to swap out the numbers in one structure to get the table to look the same as in the other structure, is called an isomorphism. It is possible to capture the idea of two tables looking the same using a formula. For example, see how if you take 0 plus 0 you get 0, and if you run that through the isomorphism you get 1, which is the same thing as if you plug the zeros into the isomorphism first, and then do the multiplication. This happens every single time, no matter which two numbers you pick from the integers mod too. So we can use this formula to check whether or not a function is actually an isomorphism. Now let's go back to the rational numbers with Terry multiplication and the rational numbers with normal multiplication. These two systems are the same in the sense that they are isomorphic, and I can now prove it. We want a function such that addition matches up in both systems, Terry multiplication matches up with normal multiplication, and we aren't leaving out any number in either system. And here it is. Phi of x is equal to 2x. Here is the proof that addition matches up, and here's the proof that multiplication matches up. And this function is a bijection from the rationals to the rationals, so no number is left out. Thus, using Terry multiplication is no different from using normal multiplication. It's just needlessly confusing because all the labels are different. Now, at this point you might be wondering, if Terry multiplication is fine, then what's actually wrong with Terry's paper? Well, ignoring all the content that isn't mathematical, the central issue is that Terry, surprise, doesn't understand how multiplication is defined, although I don't want to blame him too much. Terry says that multiplying a and b is the same thing as adding a to itself b times. He erroneously calls this the associative and commutative laws. This is indeed how multiplication of natural numbers is often described by teachers in elementary schools, for example. And the thing is, if you take this definition literally, Terry's kinda right. You take 1 and you add it to itself 1 time. Yeah, that would be 2. But in doing this, he's attacking a straw man because multiplication of natural numbers is not actually defined this way. I suspect Terry just fell victim to bad pedagogy. It's more accurate to say that it's adding a number to 0 a given number of times. It's worth noting that there's nothing stopping you from defining multiplication the way Terry describes, but then you'd lose the properties that make multiplication useful, such as the distributive property. However, I fear that the way some people respond to Terry's efforts might leave some people with the wrong impression. I agree with the views presented by this mathematician at Dartmouth. It's admirable that Terry tried to probe the basic arithmetic that many take for granted. And it's worth remembering that the question of how basic arithmetic works isn't as simple as some might think, and that creating new operations to play with is a perfectly valid part of doing mathematics. Perhaps I'll talk more in depth about this in another video. For now, that's all I have to say.